So we're going to work on this table here, which is something we've done in the past. We're going to look at how linear variables can be looked at in an angular sense. So which angular variable corresponds to delta x? So what would that
Theta.
be? Delta theta. And then what about for v? What's the angular equivalent for velocity?
Omega.
Good, which is angular velocity. And then what about for a? Acceleration. Good, alpha, which is angular acceleration. What about for mass, m? What's the angular equivalent of mass? Remember, mass is what makes it hard for something to accelerate. The higher the mass, the harder it is to accelerate something. What's the angular equivalent of that?
Momentum.
Close, really close. Moment of inertia.
Yes.
So that's I. Yeah, it almost sounds the same. So it's I. And remember, I, the formula for I, there's different formulas depending on what the shape is. If it's just a bunch of points or particles, it's mr squared. If you have a bunch of particles, you take the sum of all of them. So it'll be the sum of mr squared. But if you have other shapes, then you can look at the table that's provided to you on your formula sheet. So if you have a sphere or a circle or a cylinder or a ring or a slab, there's all these different shapes. So those are how to calculate the moment of inertia. Okay, what about force? What's the angular equivalent for force?
Torque.
Yeah, good. Torque. Perfect. And now this formula, so Newton's second law, F net equals ma. What would Newton's second law for rotation be?
Torque net equals to FR sine 5.
You're close. We're changing
Equals
the
inertia alpha times
Inertia.
yeah, perfect. So the m changes to I and the a changes to alpha. So that's Newton's second law for rotation. Torque net or net torque equals moment of inertia times alpha. So we have one more. This is today's one that we're going to cover is kinetic energy. So in the angular sense, we're going to call this rotational kinetic energy. So EK rotational. Okay, EK rotational, whereas the linear version is really translational. So you could put a T there, but if you don't put anything, it's assumed to just be translational. So the linear kinetic energy, translational, was just 1/2 mv squared. What is it going to be, do you think, for the rotational?
Half inertia omega squared.
Yeah, good. 1/2 I omega squared. Okay. So if an object is just sliding down a ramp, then it's translating. And its kinetic energy is translational, so we use EK translational, which is 1/2 mv squared, like before. So it's just translating, which means its center of mass is moving. When an object is spinning or rotating, then it has rotational kinetic energy. So instead of the 1/2 mv squared, we're using 1/2 I omega squared. Sometimes, though, objects will rotate and translate at the same time. So let's say you have a ball that's rolling down a ramp. It's rotating, so it has rotational kinetic energy, but its center of mass is also moving down the ramp as well. It's also translating. So it has both translational and rotational kinetic energy.